In a previous video, we talked about hydrocyanation. So adding cyanide to, let's say, an aldehyde. So here's an example of that. So I've got HCN, probably get there from sodium cyanide plus some acid. It's going to react with this aldehyde, attacking here at the carbonyl carbon to give me this cyanohydrin over here. We haven't drawn a potential energy surface for a little while, but here's what that might look like, right? So I've got my starting materials, SM, over here. I've got my product over here. And in the middle, there's some intermediate, probably this anion that needs to get protonated. Okay? So we can also talk about our transition state, right? So this is the highest transition state. That's the energy barrier we need to get over to do the reaction. Now, it turns out this is not the only way that these two things could react. What if my cyanide actually attacked here at what we might call the beta position, alpha beta? If it did, then we could push electrons up here and up there, and we get this. So now this has the cyanide attached to that beta carbon. We push those electrons up, now the double bond here, and we end up with an O- right here. This is called 1,4 addition because we're kind of using all 4 atoms in our chain, 1, 2, 3, 4 conjugated atoms here, as opposed to 1,2 addition, which is the last thing that we did, where we're really only using 1, 2 atoms, and 3 and 4 don't play a role. So we're going to talk about the competition between 1,2 addition and 1,4 addition. But before I do, let me point out that this isn't stable, right? Remember what this is? This is an enolate. And we do have acidic protons from our cyanide around, our hydrogen cyanide. And so the actual product of 1,4 addition is this aldehyde. All right, so now I started with an aldehyde, I end with an aldehyde. I don't have a pi bond here anymore, right? And I have a new bond over here. So this is a 1,4 addition product, or a conjugate addition product, as opposed to a 1,2 addition product. Okay, so in the past, when we've talked about competing reactions, sometimes we talk about kinetic products versus thermodynamic products. And this is a fantastic example of that dichotomy. This 1,4 product is our thermodynamic product. The barrier is higher, and so it's going to be a slower initial reaction. But once it comes over this big hill, it goes to a deeper well, right? This is lower in energy than my 1,2 product. So this, if we heat it long enough, everything should end up over here. The 1,2 product is our kinetic product. So that means that it's a much lower barrier to go that way, right? So it's faster, but it's also faster to go backwards from there, right? So even if I form a kinetic product, the kinetic product could go back to starting material and back to my thermodynamic product. Okay, so here and in general, when I do 1,2 addition with a nucleophile, so lots of nucleophiles can do this when we have conjugated ketones like this. This is a general reaction, not just cyanide, it's general. 1,2 addition is usually the kinetic product. And it's faster because it's essentially ionic, right? I've got a negative charge here. I've got a more positive carbon here. And so that's going to drive it there. However, this carbonyl compound is more stable than this kind of crowded alcohol. So this is a more stable product. This is my thermodynamic product. Okay? So let's talk about some more differences that we might see between 1,2 addition and 1,4 addition. Okay, so how do we know whether we're going to see more direct addition, 1,2 addition, or more conjugate addition, 1,4 addition? And again, by 1,2 I mean attack at the carbonyl carbon, and by 1,4 I mean attack at this beta conjugated site. We just mentioned how this is usually the kinetic product, so faster, maybe reversible though, whereas this is the thermodynamic product, slower but less reversible. Another difference is that we'll usually see hard nucleophiles attack via 1,2. So by hard, I essentially mean small, highly charged stuff. So O-, Grignards, alkyl lithium, things that we can really treat as having a big negative charge that's not spread out, that's kind of on one atom. So if you remember the SN2 kind of four-piece quadrant thing we had before, these are all pretty basic too, right? Like strongly basic, strongly nucleophilic. Those are generally hard nucleophiles. Comparatively, soft nucleophiles like to add conjugate addition. Now, soft nucleophiles, these are larger atoms, more diffuse charges, so that electron density is spread out either over a big atom or maybe spread out by resonance. Again, these are good nucleophiles, maybe not so basic. Amines, whether they're neutral amines, especially if they're neutral amines, thiols, sulfur, selenium, any of those big atoms are going to be good at this. In particular, one compound that's a really, really good and useful conjugate addition nucleophile are these cuprates that we've talked about. Okay? So here's an example. So this is a lab exercise that Chemistry 252 often does. So we take this cyclohexenone and react it with butyllithium, usually in dry ice and acetone, so negative 78 degrees Celsius, and then at the end treat with a weak acid. And our product is this direct 1,2 addition product. And we can prove that by going to the IR. You see an alcohol, you see your CC bond remain. Go to the NMR, you can see alkene protons. It's pretty much 100% this. So usually we have two partners do two reactions. So one partner just does this butyllithium addition. The other partner first mixes butyllithium with some copper iodide. And that together generates this cuprate, dibutyl or lithium dibutyl cuprate. Now when we add our ketone to that cuprate, now we see entirely conjugate addition. So your IR shows your ketone, plain as day, and you don't see that alkene anymore. So if I want, we just learned about how useful Grignard reagents and alkyl lithiums, a Grignard would also do this. Those are really, really useful for making alcohols like this. They like to add to ketones. Cuprates are really, really useful in this reaction. So if I want to add conjugate addition, which if you're keeping score, now if I look at a molecule like this, I know how to add some to the carbonyl carbon. I can add to the alpha carbon through the enolate chemistry, especially through this alpha carbon. And I can add to a beta carbon by this conjugate addition. So I can kind of add to lots of these positions around the ring. It's pretty cool.